So I was planning to give a break, but we are ahead of schedule, so I guess we could go on with dynamic programming. Okay, so what is dynamic programming? Dynamic programming is really just a technique which helps you, wait, is there another slide? Okay, yeah. So dynamic programming is really just a technique. There's nothing really to memorize about dynamic programming. It's just a technique very similar to divide and conquer, where you try to reuse subproblems that you just solved to make up to solve the problem at hand. So the idea of dynamic programming is you spend more memory to get better performance, and you save the intermediate results that you see, and then you use those intermediate results to make up the solution for the bigger problem. So a classic example of dynamic programming could be something like Fibonacci sequence. If you do Fibonacci sequence in the traditional recursive approach, clearly you would be solving the same subproblem again and again. So for example, the 10th Fibonacci number depends on the 9th and 8th Fibonacci number. And the 9th Fibonacci number is going to calculate the 8th Fibonacci number when you're on that branch of the tree. So when you come back to solving the 8th Fibonacci number again, you could just reuse the solution which you just solved before. Coming to dynamic programming itself, there are two different ways to go about it. One is the top-down approach, and one is the bottom-up approach. What the top-down approach is telling is, let's say I want to find the 10th Fibonacci number. Next, I need to find the 9th and 8th. To find the 9th Fibonacci number, I need to find the 8th and 7th Fibonacci number. Clearly, you can see that you're starting out from with the problem that you had at hand initially, and then you kept looking at these smaller and smaller problems. In bottom-up approach, what you would do is you would try, when you have to solve the 10th Fibonacci number, you would try to compute the first Fibonacci number, then the second Fibonacci number, the third one, and you build your solution up to the 10th Fibonacci number. Right? And typically, bottom-up is easier to code because you would just be using loops and probably a vector to store the results. If you're using the top-down approach, you would be having memorization where you check if you already have the result for one of the subproblem. If you don't, you compute it. If you already have the solution, you just make use of it. So in bottom-up, the thing you need to remember is to seed the values to the dynamic programming itself. So you need to give the base cases. So you say, for n equals 1, this is the answer. For n equals 2, this is the answer. And then you start the loop starting from then, and then you go on filling up your answers till the problem at hand. So the number of base cases that you need to seed in depends on the problem itself. You need to seed in just the minimum amount so that any new problem that you have could make use of these values that you just seeded. Yeah. So one of the, yeah? Yeah. Yeah. You could do that, yes. Just see whether sometimes it's okay to use an unordered map because you're going to be getting the same space and time complexity, but do you really need such a heavyweight data structure sometimes when you could just probably use a vector, for example? I mean, it's totally okay to use that, just that's one thing to consider. Like, it's tempting to go with advanced data structures like a hash table, but when you could just make use of a vector, why not? A vector of pairs, I guess it would be very similar. Yeah? Oh yeah, that's going to be there too. But complexity-wise, it's going to be similar. Like, asymptotically, it's going to be the same. Yeah, so the way to tackle dynamic programming problems. So you could use this technique. This is what I use personally when I have to solve problems. Let's say you have a problem at hand. Imagine you have all the solutions till that point. Let's say you want to find the 15th Fibonacci number. When you're given this task, don't think you have to solve this entire 15th Fibonacci number. Assume you had all the solutions up till the 15th Fibonacci number. What I mean by this is, magically, imagine you had this vector which just contained the answers for all Fibonacci numbers from 1 till 14. Given that you have these solutions, could you make use of these solutions to make up the 15th Fibonacci number? Right? If you can do that, that means you have a recurrence relation. Right? You can say, if f of n is the nth Fibonacci number, you could express f of n in terms of lower order functions, which is f of n minus 1 and f of n minus 2. The moment you get a recurrence like that, you could convert this recurrence into dynamic programming very easily, right? That's the goal of dynamic programming. So try to get a recurrence relation. If you get a recurrence relation, you're basically done in solving the problem. So the best way to go about teaching dynamic programming from here is just to solve some problems, because there is nothing really to dynamic programming as a paradigm itself. It's just a technique. So let's say this is the first problem. You want to find the minimum number of steps you need to bring a number n to 1 by performing one of these three operations. You could take the number n and divide it by 3 if it is divisible by 3. You could take the number n divided by 2 if it is divisible by 2, and you can subtract 1 always, right? You could take any number n and you could always subtract it by 1. What is the minimum number of steps you need to reduce the number n to 1? That's the question. So just think about it for a minute. Is the question clear? Any doubts? Would greedy work in this problem? Why would greedy not work? Let's take 7, for example. What is greedy in this problem? What could be one greedy solution for this problem? Could someone tell me? Yeah? Yeah. So the technique, the greedy approach to this to solving this problem would be, when you're at a certain number n, you try to divide it by 3, because dividing by 3 causes the maximum reduction to the number n. You check if n is divisible by 3. If it is divisible by 3, you go ahead and divide it by 3. If you cannot, the next best thing is to divide it by 2. You're going to try and divide it by 2 if it is divisible by 2. If you cannot do that, then you're going to subtract 1. You keep trying one of these from top to down. If one of these work, you apply that operation. Let's take 7, for example. You cannot divide it by 3 or 2. You subtract 1, you get to 6. Then you divide it by 3, you get to 2. And then you could subtract 1 or divide it by 2. Either way, you get to 1. So it takes probably like 2 steps. 7 to 6, 6 to 3, probably 3 steps. But then this seems to be the optimal solution too. So does that mean greedy works? Yeah? Yeah, this algorithm is greedy that I just, yeah. So if it works for 7, does it mean greedy is working? It probably will work for 8, 9. So one of the catches in greedy is it's very easy to come up with a greedy algorithm. It's probably easy to code it as well. But one of the things you need to be really careful is to check whether the greedy algorithm indeed gives you the optimal solution or not. That's why greedy algorithms are pretty hard to prove that they are in fact correct, but they are easy to come up with. One good thing with greedy algorithms, however, is you just need one example, one test case to prove that it doesn't work, and you can conclude that the entire greedy approach does not work. You just need one case where it does not work. So could someone give me an example where greedy does not give you the optimal solution for this problem? For what value of n will greedy not give you the optimal solution? It's not a big number. Yep. Okay, for 6, you could bring 6 to 3, 3 to 1. Do you have a better way to do this? Yeah, like greedy is giving the optimal answer in that case, right? You have to come up with a case where greedy does not give you the optimal answer. Yeah? Sorry. Yeah? Yeah, for 10. What happens when you do it for 10? What does greedy tell you to do? So you cannot divide it by 3. You can divide it by 2, so you bring it to 5. Once you bring it to 5, you can subtract 1, because that's the only thing you could do. Once you get to 4, you would divide it by 2 twice. So it took 4 steps to bring 10 to 1. Instead, if you subtracted 1 at start, you would bring 10 to 9. And once you have 9, you could just divide it by 3 twice, and then you'd get to 1. So it took just 3 steps. So you just proved that what greedy said was not the optimal answer, so the greedy algorithm does not work. Right? So how can you solve this problem now, given that greedy does not work? Yeah? Yeah, exactly. So go back to the technique that I just told you. You want to find the minimum number of steps you need to bring down n to 1. Imagine you had all the solutions till n minus 1. For example, let's take n equals 1,000, right? Imagine you had all the solutions for up till n equals 999. You knew the minimum number of steps you needed to bring 999 to 1, 998 to 1, up till like 2 to 1 and 1 to 1, right? You knew these answers beforehand. If you had all these solutions magically, can you use these solutions to come up with a solution for n equals 1,000? Yes, you can, because all you need to do now is, you know that 1,000 can come down to 500 by dividing it by 2, or you could bring it to 999 after subtracting it by 1, or you cannot divide it by 3. But then you already have the solution for n equals 500 and n equals 999. So you just take the minimum of these two, because you know that it took you one operation to get you to those numbers, and from there, you already know how to reduce 500 to 1 and 999 to 1. If 500 to 1 can be done in 12 steps, and 999 to 1 can be done in 16 steps, you would obviously pick the 500 route because that gets you down to 1 faster. And once you have this recurrence, so what is the recurrence? F of n, if f of n is the number of steps needed to bring, minimum number of steps to bring n to 1, f of n equals the minimum of f of n by 3, n by 2, or n minus 1 if f of n minus 1 is accessible, f of n minus 1 is always possible, or n by 2. So you check if n is divisible by 2. If it is, then you consider f of n by 2. You check if n is divisible by 3. If it is, then you consider f of n by 3. So you take the min of these 3 values, and you add 1 to it. Don't forget to add 1 to it. So once you have this recurrence, all you have to do is start from 1, seed the values for 1, 2, and 3. Then for n equals 4, access the previous 2 values like in a vector. Remember, these are O of 1 accesses because you already have these answers in the vector. And you keep building the answer. And when you reach n equals 1,000, you would compute these answers, and you would just get the answer. So this is the bottom-up approach, bottom-up way of doing it. So any questions on this problem? Is that clear? OK. So next question. This was the midterm question, the final question last semester. So you want to find the number of ways to tile this grid, a 2 cross n grid. 2 cross n is height 2 and a width of n. So you have these 3 tiles with you. What are the different ways by which you could tile a 2 cross n grid? So for n equals 3, the answer is 5. How is the answer 5? Wish I had a board for this. OK. Or I could just start writing here. OK. Actually knock on it. I need a pen too, right? You have a pen? I need a pen. Sorry, I don't have one. Just think about this problem. Thanks, man. Oh, yeah, thanks. OK, so for n equals 3, you're looking at the different number of ways to tile this grid over here, right? So what could be one of the ways? You could use 3 vertical tiles, right? So this is the first way to do it. The second way is you could use a vertical grid and then a square. Or you could use the square first, followed by the vertical grid. Or you could use 2 horizontals like this, followed by a vertical. And then the 5th way would be you use the vertical first, followed by 2 horizontals. Right? So this is the answer for n equals 3. For n equals 2, you would just have two verticals. You could have two horizontals, and then you could have one block itself, right? So how could you use dynamic programming for this? Yep. Sorry? Okay, so how do you break it? Are you going to break it from the middle, or you're going to break at every possible point? Yeah?
Well, we know for a 2x2 block that we can get,
3 solutions?
yeah, there's 3 possible steps. So we just, we always use the 2x2 block and then see what else we can put in there and how we replace it. That's 2.
Okay. So what would the recurrence be? Okay. So the first observation in this problem is if you were to use the horizontal grid, right? If you use the horizontal tile, can you ever use the horizontal tile this way? Like, can you ever have a case where you use the horizontal tile like this, where they are not aligned? You cannot, because the moment you don't align it, you do not have these single blocks over here, right? You do not have those tiles available, so you cannot use those. So you have to use the horizontal tiles one below the other. You do not have a choice. That's the first observation. So if you were to use the horizontal tile, they always occur one on top of each other, and that's your only way. So it really boils down to having 3 types of tiles, where one is the vertical, one is the 2x2 grid, and the other is a 2x2 grid formed using this, right? So to really apply dynamic programming, get back to what I told you. The problem at hand is to solve the number of ways to tile a 2x(n) grid. Imagine you had all the solutions to tile all possible grids starting from 2x1, 2x2, 2x3 till 2x(n-1). If you had all these solutions, could you make use of these solutions to get the answer for a 2x(n) grid? That's the problem at hand. You want to go for it? Yeah. Okay. 2 times n minus 1?
It's not. It is
I don't think.
exponential.
Yeah, it cannot be 2 times n minus 1. Okay, so one more thing. This is from my personal experience. So when you see these kind of problems, sometimes it's very tempting to see patterns in the problem. Like you just solve it for n equals 1, 2, 3, and 4, and then you start generating a pattern out of it. Sometimes that could work, but what if for a given n value you did not have a closed form solution? And if you do not have a closed form solution, then there is no way. For example, if you take the Fibonacci sequence, you cannot find the n term directly. You do not have a closed form solution, so you will have to write a program for it. And what if the problem that you're trying to solve indeed has no closed form solution, right? So it can be very tempting to generate a pattern, but try not to do that. Dynamic programming does that for you, so try not to do that. Yeah?
All over 3, I think. I think it's 2 to the n plus or minus 1 all over 3.
Yeah. So
Yeah, don't worry about that.
yeah, so this problem does have a closed form solution. One thing we realize a little later. But this problem has a closed form solution. But let's not get into that right now. So what would be a dynamic programming way to do this? Yeah?
Look at 2 to the n, or you look at n minus 2.
Okay.
You add 1, you add 2 to that. You add 1 to that, also multiply 2, you do 2 ways.
Okay.
And then you look at n minus 1, add 1 to that.
Yeah, so what is the recurrence for this? If f of n is the number of ways to tile a 2 cross n grid,
2 f of n minus 2 plus 1, and then f of n minus 2 plus 1.
wait, what are you saying?
So 2
f of n minus 2?
Yeah, and then plus 1 plus f of n minus 2, and then plus 1 is in the parentheses.
Okay, so would you do a plus 1 to this? Why would you do a plus 1?
Because the square is plus 1 current around.
Yeah, so would you do a plus 1 there? Just think about it.
Well, I put the, yeah, it's plus 2, but I put it in parentheses. Or it's distributed to 2.
Okay, you're saying this, right? Yeah. So another common mistake in dynamic programming is to see whether when you're using the previous solution, are you adding 2 or 1 to that, or are you extending that solution to work for the new one, right? So all of you understood what his approach was, right? So the last tile that you have could be a vertical tile, right? In your 2 cross n solution, the last tile could be a vertical tile. If you had a vertical tile, how many ways are there to tile all the previous n minus 1 tiles? There are f of n minus 1 ways, right? Because that's exactly what you solved. If the last tile was a square block, what are all the ways to tile the previous n minus 2 to n minus 2 grid? It's f of n minus 2. And what are all the ways to have like 2 horizontal tiles, one on top of each other as the last 2 tiles, and then you would have n minus 2 gaps, so you would have f of n minus 2 solutions for that. So let's go back to the example that we just had over here, right? So what you said was absolutely right. Let's try to solve this for n equals 4. To solve it for n equal to 4, what I could do is I could take all the n equal to 3 solutions and add a vertical tile to the end of it, right? So I could add a vertical tile here. I could add a vertical tile here, here, here. Let me just draw a line to mark, right? So if the last tile was a vertical tile, I could take all the f of n minus 1 solutions and extend it, right? Notice over here how to get all the solutions from any n minus 1, I just add a vertical tile. So you should not add a plus 1 to it. You're just taking all the f of n minus 1 solutions as they are by adding a tile to the end, right? So how many ways are there to do this? It's still going to remain 5. It's not going to be 6, right? It's going to still remain 5 because you just appended a vertical tile to all the f of n minus 1 solutions. You could go to n equals 2 and add a vertical block to each one of them, right? Or you could have 2 horizontal tiles, one on top of each other at the end as well. So if this is f of n minus 2, you take all the f of n minus 2 and append a block, or you take all the f of n minus 2 and append 2 horizontal tiles, one on top of each other. So that's going to be 2 times f of n minus 2. So your final solution is going to be f of n equals f of n minus 1, which is all these solutions, plus 2 times f of n minus 2. So there's not going to be any plus 1 or plus 2 over here. Does this make sense? So be really careful. You're not adding 1 to the previous solution like the way you did for reducing n to 1. You're appending tiles to the previous solutions and just taking them as they are. So you'd have f of n equals f of n minus 1 plus 2 times f of n minus 2. So you would just seed the initial values for n equals 1 and n equals 2, and you would have a for loop which runs from 3 and goes on till n, and then just keeps looking at these values before. So okay, so I need to get back. So any questions so far? Yeah?
Could you go over why it's 2 f minus 2 instead of like f minus 2 plus 3?
Plus 3? Okay. Okay, so let's look at how many solutions there are when you have the last tile as a square grid. So if you have the last tile as the square grid, I have to fill 2 more slots over here, right? Because I'm solving it for n equals 4. How many different ways are there to tile this 2 cross 2 grid over here? Isn't this exactly this one over here that we just solved, if you ignore this? So how many solutions are there? There are 3 solutions there, right? So you take all the f of n minus 2 solutions over here and put them over here. Or you take all the 2 horizontal grid ones, you take the last tile being this, and you need to tile a 2 cross 2 grid over there. How many ways there are to do that? You have f of n minus 2 ways to do that, right? So you take all these and you just keep adding them up. So this is f of n minus 2 ways, this is f of n minus 2 ways, and then on the top this was f of n minus 1 way. So it's f of n minus 2 plus f of n minus 2 plus f of n minus 1. So you get this recurrence over here. Is that clear? Yeah? Not really. You could pick one, but just be careful. Sometimes when you do top-down, you might have issues with the line count. And bottom-up is just simple. You won't. It's harder to go wrong in bottom-up because it's just a simple for loop, and it's easier to see that it is linear time because you know that the code just has one for loop going from 1 till n. Any questions on this problem? Raise your hand higher because I'm not able to see. Okay. No questions, right? Okay. So the laptop 2. Nathan? Which one is the source? Is it laptop 1 or 2?
Laptop.
Went to sleep. Yep, cool. Okay, so how much time do we have?
Yeah, let's go ahead.
Okay, so yeah, okay, so I managed to add the code as well.
Off by one, refresh.
Sorry?
There's an off by one, I fixed it, refresh. So close the presentation, refresh.
Is there one?
The return n is out of bounds because it was only.
Oh, the n plus 1, right?
Yeah. So,
Did I put n there?
yeah.
Yeah, okay. So looking at the code itself, the first thing you want to do is initialize a vector of n plus 1. Be really careful to initialize with n plus 1 because you're going to access the nth item in the vector itself. So make sure you make it of size n plus 1. Once you do that, I have seeded the initial two values. For n equals 1, the answer is 1. For n equals 2, the answer is 3. Right? For number of ways to tile a 2 cross 1 grid is just put one vertical tile. Number of ways to tile a 2 cross 2 grid is 3. Once you have these, you basically have the for loop running from I equals 3 till I less than or equal to n. Don't forget to make it less than or equal to n because you want to solve it for n as well. And you have answer of I is answer of I minus 1 plus 2 times answer of I minus 2. Notice how here it's not a function call, it's just two accesses on the vector itself, which are O of 1 each. So each step within the for loop takes O of 1 time, and then the for loop runs n times, so the complexity is linear. You are using O of n memory in this problem. Auxiliary space is O of n, and then you return answer of n. So the code is as simple as this, right? So one of the things with nice things about dynamic programming is once you crack the recurrence, the code is really small. It's just few lines of code, which is going to get you a lot of points. So the time is going to be spent more on solving the problem rather than the code itself. So if you do get it, you get a lot of points. Right. Okay. So the rod cutting problem. So you're given a rod of length n. It could be any unit. And then you have an array of prices that contain prices of all pieces of size smaller than n. Right? You know the price of each different cut. You have to determine the maximum value obtained by cutting up the rod and selling the pieces. So the input is the size of the rod, which is n, and you want to return the maximum profit or price that you can get out of it. How do you go about cutting the rod? Let's say you're given a vector which is price vector, which gives you the price of all lengths possible. And you're given a rod of length n, you want to know where, how many cuts to make or what are the different cuts to make. You're not interested in the cuts where the cuts are made itself, you're interested in the maximum price you can sell it for. That's the value you have to return. Yeah? Sorry? Yeah? Yeah, good point. Or else, like, how can I even give you the input? It's kind of similar to the previous problem in some ways. Yeah. Yeah, cool. That's one candidate. Is that it? Okay, so what she said was, again, using our technique, you had the maximum profit you could get from rod sizes till n minus 1. Like you knew the solution for n minus 1, n minus 2, n minus 3, down till 1. Could you make use of these solutions to get the maximum profit you can for a rod of size n? That's the problem. So what she suggested was you take the rod of size n minus 1 and put a one-piece rod at the end, right? A rod of length 1. So it's basically taking rod of n minus 1 and adding price of 1 to it, right? Price of I depicts the price of a rod of length I, right? That's the input given to you. So you just take answer of n minus 1 and add price of 1 to it. That is one candidate. Is that the best you could do? What are the other candidates you need to consider? Yeah?
Don't you have to like loop through basically
Yeah.
all n minus 1 plus, or n minus I plus I candidates for all like,
Yeah. So to really go about this problem, remember this. In the previous problem, how did you consider all the different cases? The way you did it was you looked at what could be the last possible tile. If the last possible tile was a vertical tile, you saw how many solutions were there. If the last possible tile was a 2x2 grid, you saw how many solutions were there. If the last possible tile was 2 horizontals, you saw how many solutions were there. These are the only 3 possibilities to be the last tile, right? And then you considered all the possible ways. You need to do the same thing over here. The last possible rod could be of length 1, in which case you look at a solution of n minus 1. The last possible rod, the last rod could be a rod of length 2, in which case you consider the solution till n minus 2, and then put the rod of length 2. So you keep considering all these cases. So the recurrence really is rod cut of n is equal to max of rod cut of n minus I plus a of I or price of I. You need to get the maximum out of all of these. Does that make sense? So look at the last rod. Look at how many possible scenarios are there for the last rod. It could be a rod of any length from 1 till n minus 1. You take all these rods, take their prices, and append it with the solution of the remaining part, which is something that you already have stored. Yeah?
don't you only need to iterate from 1 to n over 2?
1 to n over 2?
N minus I.
It's like symmetric.
Yeah, but then,
This one's not symmetric.
yeah.
The rods can be priced like sort of stupid.
I think
This isn't symmetric because you can't interchange
Yeah.
the
So
prices and the rod. Right?
Yeah, so what if the rod of length n minus 5 is so good that you need to pick it as the last rod, but then you wouldn't consider the other rod over here? Also remember one thing, these kind of optimizations, just think whether you're actually getting a better complexity. If you iterated from I equals 1 till n by 2, your complexity is still going to remain the same. And taking a max is not going to hurt, so as well just go all the way, right? So just take that into consideration. Like, don't try to optimize within a complexity. Like, if the solution is n square now, if you make that optimization and it still is n square, like, don't bother in the exam. Like, you probably could just go from 1 till n minus 1 and just solve the problem. You get the same complexity. Yeah? Yeah, so you would be given the option to use O of n memory in the problem, if at all there is. Like, we would give, like, if at all we have a DP question, we would definitely state what are the memory requirements. Sorry?
Or you'd be allowed to use as much as you want.
Yeah, if you don't mention, then you could use as much as you want. But the point is, like, you need to use extra memory in dynamic programming. In most of the dynamic programming problems, but some you could optimize by just using the previous values, like in Fibonacci. But then, yeah, you basically need, that's the idea of dynamic programming. You need to keep track of something which you need to get the solution for the new problem. Oh yeah, you can do that. Like, you could just keep storing the max so far, and then you could do that. Sorry? I mean, just think about, okay, so if we have asked you, we want an n square solution. If you make that optimization, does that matter? The outer loop runs for n times. You would have an inner loop which runs for n times if you kept track of max so far. If you did not keep track of max so far, you would have 2 loops which are separate from each other, your complexity is still going to remain n squared, right? But if you did the 2 loops, your lines of code might go a little longer. So just keep the expected complexity, expected requirements in mind. If you have asked you for a solution, you don't need to optimize it more than what we've asked for. So if you want a O of n squared time, O of n memory, just make sure that your solution runs in O of n squared time and O of n memory, right? Any questions on this problem? Okay, so yeah, so you'd have the base case. This is the bottom-up way of doing things. Oh, wait. Yeah, this is the top-down way of doing things because you're making a function call again. Because notice there I'm making cut route of a comma n minus j there. But then if I've already seen the solution, I just return it on the top. This is the top-down way of doing things. Is that clear? Notice how we are not making vector accesses directly. We are checking if that solution exists. We make the function call. But if we encounter, if val of n is not equal to -1, I just make use of that solution directly, right? This is the top-down way of doing things. It's encouraged to use bottom-up because it's way easier, because you literally have just 2 for loops, and then you access vectors directly. You don't need to make function calls. And it's clear to see why the solution is O of n squared too, because you have 2 for loops running in, and then that's going to be n squared, right? So any questions on dynamic programming itself? Yeah. So what's the base case for this? So the base case for this would be for answer of 1 is going to be just picking the first rod, right? And the moment you have that answer, for n equals 2, it would be the price of the 2 rod or taking the previous and then adding 1. So sometimes it's okay to put more values than required in the seeding part. That's okay. But then it's a good idea to think about what is the minimum number of values that I already need to seed into the dynamic programming part so that it could start generating the solutions from there. Typically, you do it based on the array accesses. If you need to do I minus 2, then you need to make sure that you have at least 2 solutions because you could start from n equals 3 and access n minus 2 or n equals 2. Yeah. Any other question? Okay, so next is MSTR.